Okay, look at that table, and what that's called is a contingency table. And what we have here, let me show you. They have asked people, do you use your cell phone while driving? That's a yes or no question. And have you gotten a speeding ticket in the last year? That's a yes or no question. The first question, do you use a cell phone while driving, is recorded in the rows. Okay. And the question of, did you get a speeding ticket in the last year, is recorded in the columns. Now there's 4 different cells. Let's look at these. So you see 25 people, that's highlighted green, 25 people used their cell phone while driving and got a speeding ticket in the last year. 45 people do not use their cell phone while driving and got a speeding ticket in the last year. 280 people used their cell phone while driving and did not get a speeding ticket. I feel like I messed that up, what I was saying earlier. I'm not sure. I'm sorry to waste your time, but I'm going to start over again with the green because I'm worried that I said not when I should have said they did. So let's start over again with green. 25 people used their cell phone while driving and they got a speeding ticket sometime in the last year. 45 people do not use their cell phone while driving, but they did get a speeding ticket in the last year. 280 people used their cell phone while driving, but did not get a speeding ticket in the last year. And 405 people do not use their cell phone while driving, and they did not get a speeding ticket in the last year. Okay, now, what about these numbers here? That 70 is just the 25 and the 45 put together equals 70. That tells you how many speeding tickets were gotten in the last year from these people. How many of these people got speeding tickets? The 685 is just the 280 and the 405 put together. That's how many of these people did not get speeding tickets in the last year. Let's look at those two numbers. The 305 is the 25 and the 280 together. That's how many of the people used their cell phone while driving. The 450 is the 45 and the 405. That's how many people do not use their cell phone while driving. And now finally, let's look at this number in the corner, 755. You could say that is the 70 and the 685 together. That would be correct. But it's also correct to say that it is the 305 and the 450 together. Either way, the bottom line is 755 is how many people they asked. Okay? And that should make sense. If you split the people up by whether they got a speeding ticket or not, 70 of them did, 685 did not, so that means there's 755 total. If you ask all of these people how many use their cell phone while driving, 305 do, 450 do not, so there's 755 total. Okay, and you can use a contingency table to figure out many probabilities. For instance, let's use this table and let's find the probability that a person chosen at random from these 755 people uses their cell phone. Okay? So let me write this down. Suppose we select one person at random from these 755 people. So let's calculate the probability that that person uses their cell phone while driving. Okay? Well, that's easy to see from the table. You see, it's just 305 over 755. Okay? Which can be reduced, but let's not worry about that right now. And what if you wanted to find what is the probability that the person we selected has no speeding violation in the last year? That's easy to see as well. That is 685 over 755. Okay? Let's do the probability that the person is a cell phone user who had no violation in the last year. Let's shrink this down so we can see. Okay, so I'm going to write it like this. What's the probability of uses cell phone and no speeding violation? So that would be intersection of the people who use a cell phone and the people with no speeding violation. Okay, well, let's find that in the table. Where are those people? Those people are right here. So it's 280 out of 755. Now let's do the probability that they used the cell phone or had no speeding violation. Or means union. Now you have to be more careful on this one because we don't want to count anybody twice. Okay? You can't just do this. You can't say, well, that's these people or these people and say that there is how many of those people? 990. That would be wrong. Where am I getting 990 from? That and that. That would be wrong. Do you see why that's wrong? because 280 of those people would have been counted twice. That 280 people would have been counted in that number and also in that number. So to avoid counting them twice, what you can do is there's a couple ways to do it. One way is you could say, I'm going to take that number and that number and that number and add those three numbers up. Okay, there's a faster way though. The faster way is to go ahead and add the 305 plus the 685. Realizing that you counted 280 people twice, then subtract 280 to make up for that double counting. So you would have 305 plus 685 minus 280 over 755, which would equal 710 over 755. Now, that should actually make sense to you, because that is exactly what we said in one of the previous lectures, that when you want to find the probability of a union, what do you have to do? I'm going to erase what we did. Okay, it's the probability that they use their cell phone, which is 305 out of 755, plus the probability that they got a speeding violation, minus the probability of their intersection. And that's where we get the answer. It's that plus that minus that. Okay? Now the thing about contingency tables is you don't even have to be told every number that's in there. You only need to know a few of them. Okay, let's look at an example where it's only partially filled in. Okay, look at that contingency table there. It's only filled in about halfway, but we can figure out everything that's missing. Look at the first row. Oh, by the way, let's figure out what's being asked here. So here, people are being separated into male and female. Here, people are being separated into, do they like to hike on the coastline? Do they like to hike near lakes and streams? Or do they like to hike on mountain peaks? Okay, now we can fill in all the missing numbers just based upon what's there already. Look at the first row. There's 45 total females, and the coastline and the lakes and streams accounts for a total of 34 of them. So how many must like mountain peaks? Must be 11 of them, right? Let's figure out some of the other missing numbers. I can't look at the second row to figure out these two missing numbers because I don't have enough information. But I can go by column. I can use these two numbers here. There's 41 people who like lakes and streams. 16 of them are in the female category. So how many are in the male category? Okay, it would be what's missing. 41 minus 16. Is that 25, I think? Okay. What about this missing number? Well, that's really easy. We have 11 female mountain peaks, 14 male mountain peaks. So how many mountain peaks people are there? Total 25. We can go back now, by the way, and figure out that missing number because we have these numbers. There's 25 total males, 14 like mountain peaks and 25 like lakes and streams. How many is that so far? 39. So how many are missing? 55 minus 39 is 16. So there must be 16 males who like the coastline. Okay, which allows us to now figure out that number down there. Total people liking the coastline, that's 18 plus 16, which is 34. And finally, this last number here, I can either add those together and get 100, or I can add those together and get 100. Either way, I can figure out that they asked 100 people. And there you go, we filled in the whole table. And now let's answer some probability questions using that. In order to make this go faster, let's abbreviate. Okay, we'll abbreviate female by F, male by M, coastline people by C, and let's do lake and stream people with an L and mountain peak people with an M. Okay, so let's answer these questions. This one's not so obvious, so let's think about it. It says, are the events being female and preferring the coastline independent? Based upon this information, that's all we can go off of. Okay, well, you have to remember what the definition of the word independent is. Okay, remember that F and C are independent events if, do you remember how that goes? They are independent if the probability of their intersection, which would mean the probability of a randomly selected person being a female who prefers the coastline, okay, if that probability equals the probability of the randomly selected person being female times the probability of the randomly selected person preferring the coastline, if those two things are equal, then the two events are independent. So let's simply check and see. What is the probability of F intersect C? Where is that? That's right here, isn't it? That's how many people are females who prefer the coastline. Okay, out of a total of 100 people. So that would be 18 over 100, or if you prefer decimals, 0.18. Okay. Now, what's the probability of a randomly selected person from this group being female? Well, that's right here, 45 over 100. Or if you prefer decimals, 0.45. What is the probability of a randomly selected person from this group preferring the coastline? That's 34 over 100. or 0.34. Now, multiply those two together and see if they equal this. The answer is they don't. Not equal. So that means F and C are not independent. So the answer to our question there is no. So that would lead you to believe what, based upon this sample? That would lead you to believe that there is some sort of a connection between being female and preferring the coastline. Is there really? Well, we don't know. That's impossible unless we ask every person in the world. Okay? All we can say is, based upon this sample, there would appear to be a connection. Now, it might just be the case that this sample is some kind of a misleading sample, but you have to go with the sample you have. And that's why, in reality, people draw many different samples, not just one. Okay? Let's do a question like this one. Find the probability that a person is male, given that they prefer lakes and streams. So, if you randomly select a person from this sample of 100 people, the question is, what's the probability that that person is male, given that they like lakes and streams? Let me write that down and then I'll explain it a little bit more. Okay, so first of all, I want to say this. What does that mean? So it means this. You randomly select a person. Okay, now, if I were to simply ask, what's the probability that that person is male? You would say 55 out of 100. But what if you randomly select a person and then I told you that person you selected likes lakes and streams? And now that you know that additional piece of information, what's the probability that that person is male? That's what that means. And it's written like this. The probability of male given they prefer lakes and streams. And again, if you have the contingency table, then it's really easy. 41 people prefer lakes and streams. 25 of those people are male, and so the answer is 25 over 41. There you go. Okay, it's pretty straightforward. These tables are straight out of the book, and they give more practice questions based upon the tables. So I will leave that to you. If you want to answer more questions, these are on pages 152 is the first table I gave, and the second one starts on 153, and then the questions go on to 154. Okay? All right, now one more thing to cover, and this will be quicker. This doesn't take very long at all, is a probability tree. So the example that they give in the book, and this example is right at the very bottom of 157. It says that suppose you have an urn And in there it says there's 8 red balls, oh, I'm sorry, I got that backwards. It's 8 blue balls and 3 red balls. So let's just take 5 of those and make them blue. And then add 3 more so that we have a total of 8 blue balls and 3 red balls. All right. And it says, suppose you draw 2 balls with replacement. So that means you draw one, you write down the color, you put it back, and then you draw a second one. Okay, what we can do is we can make a tree for this. That looks like this. The first ball you draw is either going to be red or blue. There's 8. Here, let's do this in blue. There's 8. Oh, darn it. Third time's a charm. Okay. There's 8 blue balls. 3 red balls. Okay. Then when you draw the second time, maybe the first ball was blue, and then you're drawing a second time after that. Maybe the first ball was red, and you're drawing a second ball after that. What would this path represent? That would represent that you drew 2 blue balls, right? And what is the number of ways that could happen? There's 8 ways that the first ball you drew could have been blue, and 8 ways the second ball could have been blue, for a total of 64. You see, I'm just multiplying, and that represents blue and then blue. Okay. What does this path represent? That represents drawing a blue ball and then a red ball. Blue followed by red. How many ways is that possible? That's possible 24 different ways. 8 times 3. Okay, you probably see where I'm going to go next. This path. That represents drawing a red ball followed by a blue ball. How many ways can that happen? 24. And then the last one, this pathway. That represents drawing 2 red balls in a row. And how many ways is that possible? 9 different ways. This is called a probability tree. And you can answer questions like, what is the probability of drawing 2 red balls? It's 9. You see that in the tree, right? Divided by what? That's the question. So let's write this, how much we can write so far. The probability of drawing 2 red balls. So here we see that it's 9. There's 9 ways that can happen. Divided by what? That's the key. All right, well, in order to find out what goes on the bottom, let's look a little bit more carefully. Okay. What is the probability of drawing a red ball? Let's maybe take a step back and write that down. The probability of just drawing a red ball. There's how many red balls? There's 3 of them. How many balls are there total? There's 11. So the probability of drawing a red ball is 3/11. So the probability of drawing red and then red is 3/11 and then 3/11. They're independent because we replace the first ball after drawing it. So to find the probability of red and then red, it's just 3/11 times 3/11, and our answer is 9 out of 121. That's the number on the bottom that we're trying to figure out. Okay? And you could answer any probability like that. You could say, what's the probability of drawing blue and then red? The probability of drawing blue and then red. Okay, well, it's right here. It's 24 out of 121. If you want to be more specific, you could say it is 8/11 times 3/11. And that's how we get 24 over 121. Okay? That's called a probability tree. All right, that's it for today.